Hey, welcome back to the lecture. In the previous lecture, we executed the linking command and we were able to successfully create the final executable, that is final.elf. Next step is downloading this executable to the target and testing our application. But before that, we have to learn some more things. First of all, when you generated a .elf file, that is executable and linkable file, you have to analyze that file to understand various resource allocation. The executable file, that is final.elf, is collection of various sections like text section, RO data, data section, BSS section. And you have to make sure that all those sections are indeed placed at the appropriate absolute addresses. How do you analyze the final.elf? Of course, there are some tools such as object dump, readelf, and other things. But you can instruct the linker to create a special file called map file. By using that map file, we can analyze the various resource allocation and placement in the memory. There is a command to instruct the linker to create the memory map file or map file, or simply we call it as map file. The command is, let's get into the make file and let's give the argument for the linker. Maybe after this, you have to give hyphen map is equal to, let's give a file name called final.map. This is a linker argument. This is supposed to be used with the linker command, that is arm-none ABI LD command. But we are not using LD command here. We are using the compiler command itself to link as well. That you can do because this executable also contains the linker driver. But sometimes what happens is some linker specific arguments are not recognized by this command. That's the reason you have to explicitly mention that this is a linker argument by using the argument -WL, and you have to give the comma. Let's try this. Let me do make clean first and make. Here you can see that we generated final.map. Let's analyze that map file. Here it is, final.map. Let's open that. From this, you can get various information. Let me explain that. First of all, it shows the memory map wherein all the sections are placed. For example, the .text begins from this location. That is correct. Like this, you have to verify. And look at what is the first section which is going to be placed at this address. That is .isr vector. That is as expected. That's why .isr vector section starts from this address. And that section actually comes from this file. That's correct. This is the total amount of bytes consumed by this section in the code memory. That is right from the beginning of this address. This is the size of that section. After that, .text section of main.o is placed from this location onwards, and the size is this much. The first function of the .text of main.o is NMI handler. After that, main follows. After that, idle task function follows, like that. By looking at this file, you can quickly identify the addresses of various functions. After that, the .text section of ld.o follows, and this much is the size. And after that, startup.o. And after that, we placed the .ro data. But I think we don't have any constants in the project. That's why it is not showing that. Let's do one thing. Here, let's create some const variable. Let's say const variable 1 is equal to, let's say, 100. create two variables here. These are the const data. Compile and see. Let's open the final dot map, and here it is. There is a RO data section, and the RO data section consumes this much. And you can see that as expected, the RO data section consumes 8 bytes as expected. The .text section ends here. If you open our linker script, after .text, RO data comes. The .text ends here, and to make an alignment, there is a padding of 2 bytes so that RO data can start from the aligned address. This is the aligned address with respect to word alignment. Word alignment is address ending with 048C, etc. This is a word alignment. That's why there is a 2-byte fill. So that is done by the linker automatically. After that, you can see that the .text section ends here. This symbol is created by us that holds this value. .data section follows .text section in the code memory. The .data section starts from this location onwards in the code memory. That's the load address of the .data section. That means eText is nothing but beginning of data section in the code memory. Here you can see that this address is aligned address. That is ending with 8. That is aligned. Sometimes this may not be the case. For example, I create one more variable in the RO data section of, let's say, 1 byte. uint 8_t const variable 3 is equal to 100. Let's see what happens. Let me build this. Let's check the map file. Here it is. Now you see the start of data section in the code memory is not aligned. So that's bad. You should never maintain something like that. It's always better to have aligned address for different sections. Here, linker will not care about using fill. Why? Because that's the end of that section. So that's why linker will not care about aligning this further. You have to do that manually by using the align command. Let's use the align command. Go to our linker script, and here align the location counter for the word alignment. That's why you have to do location counter, that is dot is equal to. You have to use something like this. That means you are assigning aligned value of location counter. Since this is an expression, this must be terminated with a semicolon. What's happening here? First, the previous value of location counter will be taken, and that will be aligned to the next word boundary. If you want to align to the next double word boundary, you can mention it as 8. But the value must be power of 2. I want word boundary alignment. The old value of location counter is taken. It will be aligned to the word boundary, and the new value will be stored back into the location counter. This is like assignment. That's why you have to use the semicolon here. Let me do make clean, and let's build. Let's check the final map. Here it is, fill. And you can see that now the data section can begin from here. That is the load address of the data section. Get back to the linker script. Here, this is the beginning of the sdata. After that, let's continue. These are some sections added by the linker. You need not to worry about that for a time being. And here's the data section. The data section begins from this address, and the data section consumes only 1 byte. That is true because if we open our main.c, there is only one initialized variable, that is current task. Only this variable goes into the data section. That makes sense. Size is 1 byte. And that is contributed by the main.o, and the exact variable name is current task, which will get placed, whose location is this one in the data memory, correct? After that, led.o consumes 0 byte in the data memory. That's correct. And there is no contribution from the startup.o as well. Only contribution is from main.o. That is only 1 byte. The sdata linker script symbol contains this value and ndata contains this one. Again, you can see that this is not aligned. Let's make it aligned, because after .data section, the BSS section follows in the data memory. What I would do is I would go to the linker script and I would make alignment here. And after that, let's continue. Let's build this. So here it is, end of data, this address, that's fine. After that, BSS starts from here. What are the contributions to the BSS section? Let's see. In the main.c, we have this variable. There is a variable which is initialized to 0, global tick count. This goes into BSS section. All these will go into RO data. How about this variable? This is an array of structures. This is a huge data, isn't it? And this data is uninitialized. This also must go into the BSS section. Let's see that in the map file. BSS section begins here, and the contribution is from main.o, tick count of 4 bytes. That's true. After that, no contribution from the led.o, no contribution from the startup, end of BSS. That means we missed this one. That means this didn't go into BSS section actually. Where did it go then? Interesting. It went into the common section. You can see that there is one more section created by the compiler called common, and the contribution comes from main.o. That is, the exact contribution is user task. That is this one. But we know that this should be BSS, because as per our understanding, all uninitialized global data will go into BSS section. That's why what you have to do is you have to slightly alter your linker script to include this section in the BSS section. Let's do that. Go to the linker script and let's edit this. I would add one more alignment here after this. Before you ending any section, so just make sure that the location counter is aligned. That's a rule of thumb what you can follow. Here you can do star common. Let's put that section common in the BSS section. Let's do make clean and make. Here it is. Now the BSS section looks okay. BSS section starts from here and ends here, totally 54 bytes. That's okay. Like that, you can analyze various things by using the memory map file. So very important file you can generate by using the linker. Let's get back to our workspace, and now let's open the startup file. In the startup file, we have some pending work, isn't it? That means we have to copy data section to SRAM, and we have to initialize the BSS section to 0. And now we can easily do, because we have got the boundaries. So we'll do that in the next lecture.